Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Larger and larger routing table size in terms of the total number of nodes in the system. For example, let's just take two typical points, chord and one hop. So chord maintains the routing table size of log n, and with one hop, it tries to maintain a complete routing table at each node. So lookup can be resolved in one step in the minimum latency possible. And of course, people analyze the lookup latency of these different protocols. And of course, as you keep a larger routing table, each node has more and more information. Lookups can be resolved much faster. So that, however, is a very static view of the lookup latency. In terms of when the nodes actually come and leave, you will have this problem called timeouts, because one node might accidentally forward the lookup message to the next hop node that is currently not in the system, has already left the system. So in terms of timeouts, these can actually be very expensive. And in particular, it needs at least one round trip time to find out that the timeout has occurred. And probably in reality, probably more, that we have the P, which is the timeout penalty. And people have used mechanisms to combat, there are like special techniques that are developed that might reduce probably timeout. So here, sorry, there's a mistake here. So for example, the academia with parallel lookups is a mechanism that when node forward lookup message, instead of forwarding along one single path, it tries to simultaneously explore multiple paths in the hope that it's very unlikely that all of the paths will be in timeout stage. But nobody really has evaluated what is the benefit of this parallel lookup. So that's the question mark should be here. So the current state of art of the protocol is, if you want to decide which protocol that you should use for the decentralized system you're building, you need to, take the spectrum and decide which point of the spectrum you want to be on. In particular, whether you want a slow but cheap protocol like chord, or you want a fast but very expensive protocol like one hop. And additionally, the even complicated thing is, it's not just the bandwidth that determines where on the spectrum you want to lie on. It's also what is the churn, the node join and leave rate in the system, and how big of the system that you ultimately want to support. So in short, if you have very few available bandwidths, or the system suffers from high churn, or you have a large system, you want to use something like chord, and conversely, you want to use something like one hop. So what we observe here is, for churn and system size, we really don't have much control with. And the bandwidth limit, the available bandwidth is actually not a condition, it is actually a constraint, because that is the ultimate constraint that limits a protocol's best possible performance. So, so what we want to do is, for the accordion design, why do we decide to design another protocol is we want this protocol to explicitly take into consideration of the bandwidth constraint that is imposed on it. So it should have some bandwidth limit. And given that bandwidth limit, we want the protocol to automatically adapt itself to optimize the lookup performance. And in order to do that, in order to have the optimal lookup performance, it needs to adapt to the size of the system and the current churn. So, and the side effect, it cannot have a rigid table geometry because it needs to arbitrarily expand and shrink the routing table size as necessary. So we envision that when users use the system, it specifies the bandwidth limit to this protocol. So let's put it more concretely what we mean by having a bandwidth budget and having the system automatically adapts. So here I have two graphs, two abstract graphs. The left graph is the bandwidth usage versus the size of system. And the right graph is the lookup latency versus size of system. And I plotted two state-of-the-art protocol in terms of fast but expensive and slow but cheap protocol. So So on the left graph, we see that really if you commit to using a protocol like one hop, what you end up is your bandwidth consumption will go up linearly with the size of the system. So if your system all of a sudden grows very popular, this bandwidth usage might exceed, your link capacity, your access link capacity, or something like that. And on the other hand, Chord's bandwidth consumption scales very nicely, scales much slower, it's log n. But on the other hand, when you have a small system, when the size of the system is small, if you look at the latency, you would assume that, when the size of the system is small, it should give you something like the best, have a latency that approaches one hop, but Chord still have quite a large lookup latency. So what we want is a protocol that have a fixed bandwidth budget, no matter what changes that you have in the node population or churn. And when the size of the system is small, it's going to give you best latency that approaches the best latency possible for one hop. And on the other hand, it's going to, when the size of the system grows, it's going to adjust its latency to approach that of Chord. So in this talk, I'm going to discuss this protocol that we designed called Accordion. It is able to match the best performance of different protocols over a wide spectrum. And in order to evaluate this protocol, we need a new evaluation framework that we designed, because most previous evaluations don't really evaluate protocols in a dynamic environment. So it really cannot take into consideration of many of the optimizations that different protocols introduced to make them work well at additional bandwidth overhead. And our evaluation is done in the framework of PDB-Sim, a packet level simulator that I co-developed. And in particular, we implemented many protocols in the simulator and has an accurate network delay model, and it's actually very widely used. So here, what is the overall architecture that we envision our protocol to be run?
So does that 100 downloads a month mean that there are 100 new people developing peer-to-peer protocols per month?
More like they're evaluating. They try to decide for themselves, like, which one is better or which of the mechanism is better. I don't think there are so many people developing lookup protocols. In fact, when we developed this, like, a lot of people asking me, is there a billion protocol already? Why a new one? So here, really, there is nothing much to our lookup protocol except a routing table, that you need to keep this routing table, you need to add entries to it, and you need to make sure that it's relatively fresh in order to avoid timeout. So what we envision is, instead of dictating what the size of the routing table should be, we break it apart into two processes. So at one side of the processes, we have a process that just keep adding entries into the table. So this is what we call the node entry addition process. And this process, we envision it to be influenced by the bandwidth budget. The more overhead you give it to it, the more budget you give it to this addition process, the faster it can learn. And on the other hand, we have a node deletion process that throw entries out from the routing table for whose neighbors that might possibly be dead at this moment. So there are a couple of challenges. Yes.
So for the node deletion process, is it the case that, is there going to be any kind of, well, this isn't my favorite node, but I'll route to it if all the other nodes are gone? Is it probabilistic, or is it going to be a hard decision where either you're alive and I have confidence in you, or you're out of the routing table and I've forgotten about you?
You will see that later. So that's just the overall, intuitive.
Okay, I can be patient.
Yes. So I'll go to that. So there are three challenges. First, what is the content of the table? What nodes should we put in the table? So in particular, we need to make sure that, when the table size is small, we can still kind of like Chord and guarantee log n lookups. On the other hand, if we do have a lot of bandwidth budget and we want the freedom to be able to add any node in this table. So we don't want a rigid overlay geometry for the table. And then, of course, I need to be able to understand what nodes to add to maintain the table content and what node to delete so that they will not give me timeouts during lookups.
There's something else I don't understand.
Okay.
So you say guarantee login lookups. That seems like a bandwidth budget that's going to grow linearly with churn. And I thought on the previous previously you told us that there's going to be a fixed bandwidth budget no matter what.
Yes, there are going to be a fixed budget. So guarantee log n lookups is more like, you can't guarantee log n lookup when you have no bandwidth budget, right? But more like when the table size is small. So we can't really say, as the bandwidth budget approaches infinitely small, we still guarantee log n. It's like we have reason, like in terms of chord, like if chord's bandwidth consumption is this, and you give accordion this bandwidth budget, it's going to approach, it's going to have a worst case log n. Yeah, okay. Exactly.
Okay.
So, and then I have this bandwidth budget, and potentially both of these two processes might incur bandwidth overhead. So I need to be able to decide, what overhead do I use it for? Do I use it for addition process? Do I use it for deletion? And before I talk about the table contents, I need to tell you a little bit about how we map keys to nodes. So this uses the same idea. It uses the idea in consistent hashing, and that chord and pastry also uses. So basically, it organizes the ID space in a ring-like structure. And all the nodes have a random IDs, for example, SHA-1 hash of its IP address. And so it sits somewhere on this ring. And similarly, the key is also mapped in the same identifier space. And in consistent hashing, whatever node that comes immediately after the key on this ring is the node that we should route the lookup to, is the node that's responsible for that particular key. And similar to chord, we use the chord structure so that each node at least maintain the successor pointer on this ring. So it's guaranteed that the lookup will always be able to go to the successor for that key. And in particular, we also use the notion that the ID distance between two points, either two nodes or one node and the key, is simply the ID distance that's clockwise, and that's the clockwise distance on this ring. So let's do some conceptual exercises, see what kind of table contents might we want in order to guarantee low hop count lookups. So here, the red node is the node that we are currently considering, and here's the key. And so these hollow triangles are the table contents for the red nodes. So obviously, we want some table contents that point to faraway places on this ID ring. And therefore, it guarantees us that the first hop can take a quick jump towards the right direction in the ID space, towards the key. So now we reach this second hop, this blue node. And if the blue node still only has routing entries that point far away in the key space, in the ID space, it's not going to help us much, because we are going to overshoot the key and kind of result in random search. So what we need is also a couple of routing table entries that also points to ID space that are close to itself. And so it can keep making good progress in the ID space and finally reach the key. So in general, like the table contents, the kind of characteristics that we want to have for the table contents is nodes should preferentially know more about routing entries that are close to itself in ID space than farther away. So that's the general feature we like. And formally speaking, this is what we call a small world probability distribution. So instead of using a rigid table geometry, we use a probability distribution that's originally proposed by Kleinberg. And formally speaking, it simply says a probability that a node having a neighbor entry that is x distance away in ID space is inversely proportional to x. So this has the feature that that the nodes will preferentially know more about other entries in ID space that's close to itself. So this guarantees log n lookup hops. And here, let's see visually what this small world distribution might look like. So here, in a 5,000 nodes, if this red node samples 20 nodes from the probability distribution, that's what its routing table will end up look like. And this is what happens when samples 50, and this is what happens when samples 100. So you can see there is always freedom for this red node to know everybody in this in the entire network if it's able to sample enough of the table entries. But then when the table size is actually small, it's going to know more about other entries that are close to itself in ID space. And here, I'm not going to give the formal proof And I'm just going to intuitively explain why this small world distribution guarantees log n lookup hops. So here, this red node has the small world distribution routing table. And it's to forward the lookup message, it simply forwards the routing table entry that is closest to the key, but still precedes the key on the ID ring. And with a small world distribution with high probability, this first hop is going to be able to cut the distance between the current node and the key by half. So when it reaches the second hop, that is the blue node here, the blue node also preferentially know more about other nodes close to itself than far away. And therefore, the probability that it is continually be able to cut the distance between cut the forwarding distance between itself and the key by half is still the same. It's still with high probability. It can cut the distance by half. And so, it forwards to this green node, and the green node still going to make the same kind of progress that finally reaches the key. That finally reaches the successor for the key. So basically, with high probability, with every hop you take, you're able to cut the distance between the current node and the key, the lookup key, by half. So on average, you're going to take log n lookup hops. So here, I've already summarized what the table contents should look like for Accordion, and I'm going to tell you a little bit more about how we decide what is the addition process look like in order to fill in the routing table entries. So the most obvious approach is to simply, periodically, I'm going to look up identifiers sampled from a small world distribution and look up routing table entries, around that key. However, this is actually expensive because whatever overhead traffic that you send out, those are purely overhead. They don't help you in doing anything else. That's just pure overhead. So a more efficient approach is, by observe, since I'm doing a lot of the lookup traffic anyway, I might learn something as a part of the lookup instead of, having to go out of my way to acquire table entries. So for example, we can, yes?
Why would you, it seems you say you're going to learn about the target node. What about the source node? Because the target node might not be there. The source node of the lookup is there. It just generated the lookup.
Yeah, sure. Source, target, whatever information, whatever site information you can get. Yeah, so the efficient approach is whatever information you can get from lookup message, always put it in the routing table because they're there anyway. But however, the problem is if I just purely rely my addition process on this lookup message, it's not going to guarantee to give me a small world distribution because the lookup keys are more likely to be completely uniformly random in the ID space. So what Accordion does is somewhat more active than just purely passively snooping on the source and destination addresses of lookup messages. So,
another question?
Yes.
Do the lookup targets that happen to pass through your node, also do they have the uniform distribution in key space? Or is it the case that more lookups come through you to nodes that are close by?
In terms of the destination, the key destination, like the key, is completely uniform, right?
Right.
But your observation is exactly correct in the sense that when I forward lookups, most of the lookup hops are actually small in ID distance. Basically, when you look at the lookup key, you're going to see more lookup keys that are close to you in ID space than far away. So that is exactly the intuition that we use in order to learn according to a small world distribution.
Okay.
Yeah, but you don't really learn the key, right? Because you want to know the entry that's around that key. So.
Right. It's that you're seeing the key, but you want to know the value.
Yeah, I want to know the IP address that corresponds to the key. Yes. So here, just as Donegan says, you notice that when you forward lookups and when lookups are uniformly random, you are going to pretty much use a random node from your routing table. And the random next hop you use, since they come from your routing table, is going to have a small world distribution. So here is, you look at the source and destination of the lookup. It might not be might not have a small world distribution, but if you look at the next hop you use, it's going to, you are going to use more of the next hops that's close to you than far away. So here, this black node forwards the lookup message to the red node, and then red nodes keep forwarding the message by taking a next hop from its routing table. And so with the next hop, that is the blue node, is going to keep forwarding the lookup message. But however, to help the previous hop learn more information according to a small world distribution, this blue node is going to examine this ID region between itself and the key. Because it knows, for one thing, it knows that the previous node knows nothing about that particular region, knows no entries in that region. Yes?
Maybe I missed something, but it seems like there's a discovery step missing from here somewhere. In other words, it seems what you're describing is if you have a routing table, then this is how you learn more information when the routing table gets used. Mm-hmm. Where did that sort of seed routing table come from? How do you even know which IP addresses are in the key space to begin with?
Well, the thing is, a small world distribution is a stable distribution in the sense that if you start with a small world distribution and keep learning more information like this from it, it's going to end up in a small world. But we also show, like empirically, that even if you start with a random routing table and learn in this fashion, you're going to end up with a distribution that looks like small world. But we don't have proof for that.
I'm asking, I think, a much simpler question.
Okay.
Let's say the node just turned on.
Yes.
It has no information in its routing table.
Yes.
You get a lookup for key 43. What do you do with that? You don't even know which other node.
The node needs some, like a initial starting point to contact in order to know some other nodes in the system, but it doesn't matter what.
So do you have to seed it then with
you have to seed
random
it.
nodes?
Yeah, exactly.
You need some index somewhere of nodes randomly picked from.
Correct. So basically, currently what the system does is always have a couple of nodes that's pretty well known. So every node, when it starts up, it contacts the well-known node, and the well-known node can simply just tell it one other node in the system, or a bunch of other nodes in the system. And from that, bootstraps the node.
So initially, every query then just goes through the well-known node, and then you start to learn more details about the routing table as you see responses to those.
No, I don't think the queries go to the well-known node.
I mean, the places where you forward your queries to.
Oh, yeah. Initially, if you do not know anybody, you have to forward, but you can very quickly build up the routing table.
Why does a query ever get forwarded to you if you're not a well-known node?
Oh, because as you see, like when you have a join, so actually each node has a join process. So you first try to join by notifying the predecessor node and the successor node on the ring by itself. So you notify them, and they will spread the information about you around. And also, as you perform lookups, other people will know about you.
Okay. So
that's how everybody else in the system gets to know you. So, what this blue node does is, look at the ID region between itself and the key, and picks up a number of additional entries, IDs and IPs, and piggyback it to the acknowledge message. Piggyback it on the lookup acknowledge message that is going to send back to the previous hop anyway. Is that clear?
I understood that.
Okay. So, so if we look at what the contents of the routing contents for the red node now, these three pink nodes are the three additional nodes that's added to its routing table after that particular lookup message. So this is how we acquire the table entry. And so we decide to use, we have analyzed, and decide that the best way to use the bandwidth budget is to try to use all of the bandwidth budget in learning new information. And to learn new information, since we know that we can rely on lookups to help us learn, so we decide to try to use as much bandwidth budget as possible purely for lookup purposes. And when the lookup rate is actually small, we can increase the lookup parallelism of the lookup messages to help us. So for one thing, it can help us learn more to add more nodes in the routing table. On the other hand, because we already discussed, parallel lookups can actually mask the effects of timeouts, because when you send lookup messages among multiple hops, multiple next hops simultaneously, it's very less likely that all of them going to be in timeout stage. And so what Accordion does is periodically it's going to, based on past observed lookup rate, adjust lookup parallelism to try to fill in the entire budget. And of course, lookups are bursty, so we cannot expect to do this perfectly. So whatever bandwidth that is left over, we use that to just simply actively explore for more routing table entries. That is the addition process that we just talked about. And in the next, I'm going to describe how we are going to do the deletion process, how we are going to decide to throw entry away from the routing table. We need to do this proactively. Obviously, you say that whenever I incur a timeout during lookup, I have to throw away entries from my routing table. But that is already, by that time, it's already too late because the timeout has already happened and you have increased your latency. So what we need to do is to delete proactively before a lookup timeout happens. And you decide that one way to do this, obviously, is to periodically ping your routing table entries to make sure they're still alive. But that is actually very expensive because whatever bandwidth we used for pinging, we could have used the same bandwidth to acquire additional state. So what we do is for each routing table entry, we are going to predict what is the probability that that entry is still alive now, that the node that corresponds to the entry is still alive now. And we are going to delete all the entries for whose P alive is less than a predetermined threshold. So how aggressively should we delete table entries? So intuitively, this is very easy to explain. So on the axis, we have 2 points. On the right, we delete very aggressively, try to make the table entries as fresh as possible. On the right and the left side is we delete very lazily. And if we look at the lookup hops plus timeouts, what we see is if we delete too aggressively, we end up deleting nodes too fast from a routing table. So we are going to end up with a very small table, and this will result in many lookup hops. And on the other hand, if we delete very lazily, we know that of course, you can maintain a large routing table, but they're not very fresh. So you're going to incur a lot of timeouts. So when you add the lookup hop plus timeout together, you're also going to go through the roof. So clearly, there is something in the middle that is actually a minimizing value for this deletion, for how aggressively we should delete the table entries. In fact, you can do this analytically by trying to derive what is the table size at equilibrium at the addition process, and deletion process will form an equilibrium. And you can analyze analytically that, what is the table size at equilibrium and how fresh it is. And you can plot on this graph. On the x-axis, we have, you delete what is deletion threshold? That is, you delete entries whose probability of alive is less than x. So the right-hand side is delete very aggressively, then the left-hand side is delete very lazily. And you have this bathtub-like shape of curve and has a minimizing point, and somewhere between 0.8 and 0.9. So we pick our best deletion threshold to be 0.9. So now I've talked about what is the node to delete. We still need to try to estimate the value of P alive to predict what is the probability that the neighbor is still alive. So we can throw away entries with low values. And so firstly, we notice that to predict what is the probability of the node still being alive, we need to know something about the distribution of node lifetime. And in particular, we notice one common characteristics among many node lifetime distributions is that nodes that have been up for a long time are more likely to be up at the time you're considering. So this is empirically validated by the Gnutella node lifetime trace. And we took that trace and found that it actually approximates a Pareto distribution reasonably well. So we know that is the node lifetime distribution. It has a Pareto-like heavy tail distribution. And so what are the information that we can easily learn about each entry to try to estimate the probability of the node being alive? So we can easily learn 2 pieces of information. First is when was the node last booted? And secondly, when was the node last known to be alive because some other node in the system has contacted that node. So if we look at the timeline here And we know some node in the system, maybe not us, has contacted the node at some point in the past. So that's the last contacted time. And we know that the node was last booted somewhat some time ago, and we can calculate the U to be the known uptime, which is the time interval between boot and last contacted time. And given that we want to estimate what is the probability that the node is still alive now, we also need to calculate what the age of the routing table entry, which is simply the time since the entry was last known to be contacted by some other node in the system. So given that we assume that the node lifetime follows a Pareto distribution, we know that the probability of the entry still alive is basically equal to the probability of that neighbor having a lifetime greater than U plus A. Given that we already know a piece of information that its lifetime is definitely greater than U. So this is equal to U over A plus U. So this has very intuitive explanation. For example, the bigger the U, that means the longer the node has stayed up, the bigger the P alive is. That means the more likely the node is still up now. And also, the bigger the A, we know, that means the longer the last time since the node was last contacted, that means the older the age of the routing table entry, the less likely that that particular neighbor is still alive. So after we have calculated the P alive for every single table entry, we're just going to delete the entry if the probability of alive is less than 0.9, less than the threshold we picked. So putting everything together, basically, Accordion, for each of the routing table entry, it also maintains the age of the table entry and also the last known uptime for that particular entry. And it's also going to propagate this information to other nodes as other nodes learn about each other. So basically, Accordion never explicitly commit to a routing table size beforehand. Rather, the routing table size is an equilibrium of the addition and the deletion process. And the bigger the bandwidth budget you give it to it, the bigger the routing table will be. And the greater the churn is, the faster the entries are deleted from the routing table, so the smaller the table size will be. So now, I need to evaluate this protocol against our original goal of trying to match the best performance of existing protocols over a wide spectrum. And we also like to see how well it adapts to the size of the network and the churn. So to do this, we actually face a number of challenges. For one thing, there is no existing framework available to evaluate performance of protocols under churn. And in particular, there is lots of different performance metric proposed, and many of these protocols have, like little simple techniques like parallel lookups, proximity neighbor selection. That is, it generates extra overhead, but it also lowers the lookup latency. So we don't know how to. We need to find a way to properly charge for these expensive optimizations. And thirdly, we don't know. Many of these, Accordion has only one simple parameter, that is the bandwidth budget. But for any of the other competing protocols, there are a wide range of parameters that you can set. We don't know how to set the parameters for these protocols. So first, we need to know, I wish I could present you one single number that just evaluates the performance of Accordion, but I cannot, because really the performance of Accordion depends on the bandwidth budget you give it. So if on the x-axis I have the bandwidth budget, and the average lookup latency of Accordion will just be a curve. That is, it has one single lookup latency for every bandwidth budget you give it to the protocol. So it's really a performance curve rather than a single value. And for Accordion, we have the bandwidth budget. For all of the other protocols, we have lots of other protocol parameters. For example, the dimension of the hypercube, how fast each node refreshes the routing tables, what is lookup parallelism, etc., etc. Nobody knows how to set it. So what we did is for all of the other protocols, we are going to simulate all the parameter combinations. So we are going to plot a scatter plot. This is for one example protocol. And for each one of these points corresponds to one particular parameter combination for that protocol. So on the x-axis, we plot the measured bandwidth consumption for that parameter combination. And on the y-axis, we plot the average lookup latency that results from that parameter combination. So we really have a scatter plot of all these parameter combinations. And if we look of all these points, all the points towards the lower left are the better points because they give you lower bandwidth consumption and lower lookup latency. So lower lookup latency corresponds to better performance. So if we draw a convex Hall segments among these scatter points, we can extrapolate the best possible performance versus bandwidth overhead trade-off of this competing protocol. And we are going to use this convex Hall. So what we did for the simulation, we have this peer-to-peer simulator, and we inputted a variety of protocols, including our own. And for the topology, we use 1,000 nodes, and each node, and the pairwise network delay between these nodes are the measured network delays between 1,024 DNS servers using the King method from UW. And in this network delay matrix, we have the average round-trip time to be 178 milliseconds. And we also need to feed this protocol the workload. One particular workload we use and is using the Nutella node lifetime distribution. In that trace, we have the median node lifetime to be an hour. And the lookup load is each node issues a lookup message with a mean 10 minutes. And so we simulate all combinations of the parameters and outputs the convex Hall for that protocol. So here is how existing lookup protocols do. So we have the 5 different protocols that has been proposed in the community, and these are the convex Halls for them. So on the x-axis, we have the bandwidth consumption. The y-axis is the lookup latency. So what this says is it's not like we can actively tune the bandwidth consumption of different protocols. We cannot. What it really says is, for example, all these convex Halls go up to the left. What it says, we cannot find any parameter combination that is able to simultaneously give us low lookup latency and low bandwidth consumption. And in particular, we can see the one-hop line stops stops to the left because for one hop, it tries to maintain a complete routing table at all the nodes in the system. And therefore, given a particular churn scenario, there is a minimum bandwidth consumption that it is able to use. And all these convex Halls go down to the right, and with the best performance possible is one hop approaches the average round-trip time in the network, that is 178 milliseconds. And of all these lines, in order to compare them, we know that all the lines toward the lower left are better. Because take the example of Calypso and Cademia, the Calypso line lie towards the lower left of Cademia. What it says is there is always, for any bandwidth consumption, you can always find a parameter setting that is going to allow Calypso to give you lower lookup latency than Cademia at the same bandwidth consumption. So apply this reasoning, we can see that Cord is the best protocol when you have a small amount of bandwidth, when you're consuming a small amount of bandwidth, and one hop is the best protocol when consuming a large amount of bandwidth. So how does Accordion compare with these two best protocols? So here we show the scatter plot for Cord and one hop by varying their different parameters. And for Accordion, we don't need to do this same parameter exploration trick. We just need to set the bandwidth budget to different values and see how it adapts itself to give us the lookup latency. So for Accordion, it's just a line. And we can see that Accordion approaches Cord's performance when the bandwidth budget is small, because it is able to adjust itself to use a very small routing table effectively. And when the bandwidth consumption is big, it approaches the performance of one hop. So So why is it able to do this? So here we look at, as we say, the key is to able to adjust routing table size based on the bandwidth budget. So here I show the average bandwidth consumption, and for one hop, of course, it's always the maximum table size. And it's not going to change with respect to bandwidth consumption. And for chord, these points actually corresponds to the different points on the convex hull of the chord protocol. So in fact, if you give chord more bandwidth budget, you need to tune chord's parameter to be able to use a larger routing table size. But since chord has a fixed geometry, so there is restriction on how big the what is the routing table, what is the size of the routing table it is able to effectively use. So as we can see that as you give more bandwidth budget to Accordion, he can learn about other nodes very quickly and form a much larger routing table than chord very quickly because it has no rigid geometry restrictions. So that's for one particular workload and one churn scenario. So here, I'm going to show Accordion's performance with respect to the different size of the network. So on the axis is I have the number of nodes in the network, and the left graph shows the average lookup latency, average bandwidth consumption, and the right graph shows the lookup latency. And we can see that, with respect to the number of nodes in the system, the bandwidth consumption of one hop is going to grow linearly, and chord grows logarithmically, while with Accordion, if you set it to a fixed bandwidth budget, it is going to hold that bandwidth consumption constant across different size of the network.
I have a question.
Yes?
I thought earlier you said that Accordion always did at least as much as chord because it still guaranteed login lookups.
Mm-hmm. So
then here it doesn't because there's a red point that's higher than the green point on the right of the graph on the left.
Oh, this is so previously I have the flexibility of setting chord to one best parameter. Mm-hmm. So here what I did is the chord's parameter is fixed. Chord has a fixed parameter. And so with Accordion, the fixed parameter is just the bandwidth budget that holds across. So if you look at the latency here, that it's going to have the latency that approximates one hop when the size of the system is small, and the latency will grow as the system grows because it's trying to keep the bandwidth consumption constant. It's going to approach chord. Yes?
What is that parameter in chord that you're keeping constant? How do you
Everything. There are like multiple parameters. So basically, I find one best parameter for chord for a 1,024 node network, and I'm not going to set it differently for different sizes of network.
So is that like base?
There is base, there is successive refresh interval, there is finger refresh interval,
So
there's
is
how
it
many nodes you sample for proximity.
Okay.
Yes, 4 parameters.
Okay.
Yes, for any number of these protocols, typically you have 4 or 5 parameters. Actually, some of the parameters are not useful. We can use this framework to also analyze the importance of different parameters, but I'm not sure.
So the scatter plots that you showed earlier, that was for a single topology and a single workload, and you were walking for different values of all 4, different combinations of all 4 of those parameters.
Yes, exactly. So here I show how Accordion adapts to the churn. So here I vary the median node lifetime in the system, and further towards the right, I vary it from half an hour median lifetime to almost 4 hours of median lifetime. So here you can see that the bandwidth consumption of Accordion, given a fixed bandwidth budget, is going to remain constant over the churn. Yes.
So previously it was a trace. Is this the trace kind
of compressed? This is the trace, but compressed. Like, we set the median lifetime to be, say, if we set the median lifetime to be 20 minutes, we're going to compress everything by dividing.
You also compress the query load, the lookup rate?
The lookup rate is not compressed. The lookup rate is same. So in the sense that, yes, you're right, when the churn is higher, the lookup rate is actually, the lookup rate is actually higher. So the lookup rate for this is actually higher.
So you also compress the lookup rate?
I did not compress the lookup rate, but So basically, the lookup rate relatively to churn is it will be higher here and lower here. But I also vary the lookup rate. I actually vary the lookup rate for fixed churn, but I'm not showing the result here. It's similar.
If you don't vary the lookup rate, do you ever run into a problem where your trace says that a node that's dead is going to issue a query?
That's why I say the lookup rate is, but the lookup rate is still like much smaller than the median. The mean time between nodes issuing query is still much smaller than the mean time the node is going to fail. And in the trace, a node that's dead never issues a query.
What?
You could just cut that off post factor, right?
Yeah, I agree.
Yeah, there's no. So basically, in each node's lifetime here, the node is going to issue more queries. You're absolutely right.
Okay.
Yeah. But yeah, so with core and one hop, you can see basically, the bandwidth consumption is going to scale linearly with the churn rate, so it basically scales inversely with the median node lifetime. And Accordion is going to be able to hold that constant. And for the lookup latency, when the network is stable, it's going to approach the performance of one hop. And when the network is very unstable, it has to keep a much smaller routing table size. So it essentially approaches the performance of core while it's holding the lookup, holding the bandwidth consumption constant. So there are many, yes?
I just wanted to ask one more quick question for you. So in some cases, a lot of these curves that you're showing are close together, and each point represents an average, but there isn't like an error bar there. So I don't have a sense for if the variance, how big is the variance in those points relative to the distance between the curves?
Oh, so we look at the 10 percentile and the 90 percentile. The 90 percentile, I think, is slightly less than twice of this average.
So off the chart, and then in this case, so like if the average is, let's say, 200.
That is the same for all of these three protocols, though. We look at the variance.
So you're saying if you look at the 90th percentile, it'll be the same curve, but doubled on the scale of the graph?
Pretty much. Yeah, that's why we look at the average, because we initially look at the median, but then the median is a lot of the protocols. For example, especially one hop, the median can really have very low medians, but the variance is much higher. So there are many lookup protocols that inspire Accordion, and Accordion uses a technique like parallel lookups and learning from lookups from other protocols, drawing lessons from other protocols. And there are also many different ways of doing evaluations of, among these different protocols. And the key difference of our evaluation framework is we very explicitly consider the bandwidth overhead of each protocol. And therefore, it allows us to implement and actually take into consideration of many of the bandwidth expensive optimization techniques that these different protocols propose to make them work better, and to just try to understand if it is actually effective or not. So in summary, a key-based routing is a very effective way to find information quickly in a decentralized systems. And however, the best strategy is not, it really depends on the bandwidth available, the size of the system, and the churn. And the existing protocols really target one single environment. And what we did is we designed a protocol that is able to adjust itself automatically to different environments. And our evaluation shows that it matches the best existing protocol performance over a spectrum of environments. And stepping back, what I really learned from designing Accordion is really this notion of explicitly taking into consideration of the cost of a distributed protocol. And when you really have to consider the cost of the system, you're able to design mechanisms that is able to use that fixed bandwidth budget more effectively. So now I'm going to throw in 2 slides about the system that I'm actually building now that is going to use Accordion. It is the decentralized distributed digital library that we call Oversight. So CiteSeer, you guys probably all know, is this very popular online research paper repository. And it is today it's very resource intensive for PSU to host this size here. You probably know the performance is pretty bad these days. And because it serves a 250,000 keyword searches per day, and that is also because the system really it's overloaded all the time. I'm sure if the system capacity is actually bigger, you'll see more keyword searches, and more data transfers. And it currently transfers 34 gigabytes of data every day. So what we are doing right now is to build a decentralized system that we call Oversight that we envision the system to run on hundreds of donated machines over the internet. And so the architecture of each of the server is, it will have a DHT that consists of the Accordion Lookup protocol and the storage maintenance layer of dhash. And of course, it's going to have a crawler, a web-based front end, and a distributed indexer that is going to help us to do the keyword searches more effectively. So I have worked on the algorithm for doing distributed keyword search. So that is a very different problem than just a simple lookup. Because with the simple lookup, it's really a one-dimensional lookup. You have a key, and there is only one dimension to that key, and you look up the node responsible. For distributed keyword search, often you issue keyword lookups for multiple keywords. You want to do a join. So it's a search in a much, much larger dimension. And I've analyzed this and find that really full text search for the whole world, for the whole web, is not very practical unless you devote significant wide area network and disk resources to it. And what saves us here is Oversight has a much smaller index than the entire web. In particular, even though Oversight has more than a terabyte of data, and its index is actually relatively small, it's less than 20 gig. So what our current design is to partition the index by document to parallelize queries, and we're also going to replicate this index on multiple machines to increase the throughput of the search. So looking even further into the future, I think many of the ideas that I've learned in designing the peer-to-peer lookup protocol is equally applicable to network routing, especially when we have to consider the overhead of the routing protocol. Really the performance of the distributed protocol is not a fixed point. It is constrained by this overhead you're willing to spend for the protocol. And on the other hand, a very completely different project is, currently we observe that for peer-to-peer systems, we basically essentially have two trust models. On the one end of the spectrum, we have Nutella kind of like network, where nobody trusts anybody in the system. So we can only build very simple file sharing applications, very simple applications that doesn't require much trust at all. On the other hand, we have Oversight model. Basically, there is what we call every node trusts every other node in the system. And we really need that, what we call the centrally managed decentralized system. So clearly, that would be nice if there's something in the middle, in particular, if each node in the system can explicitly annotate the link, saying that what are the other nodes in the system that we trust to form a social overlay network that mimic the social links between the users themselves. Maybe we can, to capture these trust relationships, to explicitly capture, maybe we can build more interesting applications. For example, the application that we're currently thinking now is backup and private sharing. So this bears, somewhat to the design rationale for SkipNet, which, also tries to capture the trust somewhat in the overlay network. Is that true? Yeah, that's all. Thank you.
Great. I have some more questions.
Yeah.
So after doing your work on Accordion and finding that you can get good lookup via using that model, good lookup latency by using that model for capturing, who to keep in your routing table, what do you think now? What does that say about things like proximity neighbor selection and network coordinates?
Proximity neighbor selection is still important in the sense that when the routing table size is small, you need that to have good performance. So basically here is what we do proximity neighbor selection. So it's really useful when you have a small routing table size. Otherwise, you have log n times the round trip time, latency. What we do here is here, when the node actually forwards lookup and picks a number of nodes to return back to the previous hop, it picks one that have low latency based on coordinates.
Oh.
No low
Okay.
network
So you do
delay.
use proximity neighbor selection.
Yes.
Okay. So how does proximity neighbor selection interact with the looking for the small world distribution? It seems like it introduces a bias there. Or am I just wrong about that?
So the thing is, small world distribution really only helps you when you have a small table size. When you have a large table size, you're going to say you have a complete table size. It's no longer small world, right? Because you know everybody in the system. So it really doesn't really help you much when you have a huge routing table size that almost capture everyone in the system.
So is another way of saying it that the small world distribution gives you your lower bound, and then everybody else you throw in as. Okay.
Yes,
Okay.
exactly. Yes.
Trying to understand, there seems to be at least 3 things going on. The bandwidth usage, at least 4 maybe. Bandwidth usage, the routing table size, the rate of change of the tables, and the latency.
What
More
is
than
it?
3.
But more than 3. So in the sense, like you talk about how latency and bandwidth usage, have you looked a little bit deeper? You see how the 4 things
How they
relate to each
interact?
other? Yeah, how do they interact or maybe intuition maybe?
So really I would only say there are 2 things going on. If you don't want to commit to a fixed table size beforehand, you really just have the addition process and the deletion process interacting with each other.
Right, that influences the rate of change of the table.
Yeah, so basically your bandwidth budget influences your addition process in the sense that the more
Right.
budget you give it, the quicker it adds entries in the table.
Right.
Yes, and the deletion
But depends,
process.
if you have a big table, it may be, depends, right? You can either scale time or scale size,
I don't.
or your bandwidth. Like we have small tables, right? If you
Correct.
fix it, then you can change the time, like how often
Yeah,
you
yeah.
But
that.
if you
You mean fix the time you change, you refresh
well,
it.
for the different bandwidth, right? You can either play with time or play with amounts of data, right? Right. So
Play with how fresh you want to keep the routing
right,
table.
or pair,
Yeah,
how many
exactly.
entries you're going
That
to
is that is exactly basically this graph here. So we say when we add, we just always add stuff, and then with the deletion, if you delete too fast, basically delete aggressively means your table size is very very fresh, but you're only going to keep a very small table.
Right, that's in time. Talk about the size of the number of entries on the table. It seems to be all varies inside this graph.
Yes.
You can get a sense of what's going on underneath it. At least that's just my feeling.
Okay.
I have a question which I think is
Yeah, I'll see
related
that.
to this question, and that is that, is it fair to ignore the memory cost of your routing table?
Yeah.
Well, we think it's fair because like.
It's a good idea. I don't know what fair. What I mean by fair is it a good idea?
I think if you have a routing table size of, say, more than 10 meg or even 100 meg, you're going to hit bandwidth problem more, like before you hit the memory problem. That's what we think. With 100 meg of routing table size, I think you're going to.
Well, what did you see in your work? I mean, with certain bandwidth budgets, what routing table size did that lead to?
We see that with Accordion, I think we are not going to, the bandwidth budget can be. You're right in the sense that if the network is extremely stable, okay, something like say Google, right? You're going to have a huge number of entries in your routing table. And on the other hand, you only need a very small amount of bandwidth budget to keep that up to date. So yes, in that scenario, you are going to hit memory problem.
I actually have
Yes,
more
that's
related
true.
to
That's
that
a fair
one now.
question.
So it just occurs to me that memory use might actually scale as network size. That is, if you fix this threshold, let's say you want to delete it always 0.9, and you fix bandwidth, if the network is really huge, you're going to be using 100% of your bandwidth to constantly be hearing about new nodes that are very unlikely to be dead. you're just always going to be hearing at 200K per second, whatever, about new node, new node, new node.
Mm-hmm.
And none of them will be below that threshold because, we're imagining the network is basically infinitely sized.
Okay.
And so every packet you hear is about some new, very fresh node that's unlikely to be dead. So it seems like the memory then could grow.
Yeah, I think you can definitely cap the size of your memory too. So basically what the capping would be done is you will preferentially throw away nodes that, that's going to, you have a small world distribution that you want your table size to be in. Whenever you want to throw away other nodes, you want to preferentially throw away nodes that are far away in ID space than you are to make sure that you still have this, to make sure that when you want to cap your memory usage, you're still going to have good lookup performance. But yeah, that is absolutely, so I think that has a very simple fix. Yes.
So I have a question about the evaluation methodology. So it sounds like the latencies are taken from among DNS servers, and for like the oversight application, that makes sense. Then the query workload is taken from Gnutella. Does that also map appropriately to the?
No, we in our evaluations we also have a workload that has 100 times more the lookup load. So basically, we find that, for example, for systems like Core, it's actually not good because the routing table size does not grow bigger as an effect of greater lookup rate. So that, well, in fact, because every lookup is a multi-hop lookup, that amplifies the lookup rate. But for Accordion, this is actually very nice because as your lookup rate grows, the routing table size grows. So each lookup is going to take fewer hops. So effectively, the amplification is not as big. But yeah, so yeah. So we done evaluations on that.